Hi, in this topic 3, we are going to talk about the OLS and the assumption of classical linear regression model. OLS regression is a classical way to examine the relationship between two or more variables. We seek to examine the nature and the form of the relationships among two or more variables. But in this topic, we are going to consider only one dv and one iv. dv is always denoted by y and iv by x. So let's assume x and y are linked by a simple linear relationship where their population equation is given by the expected value of y is a function of alpha plus beta x. So the expected value of y denotes the average value of y for a given x and unknown population parameters alpha and beta. If we have a data set, then we can use OLS regression to estimate their relationship. So OLS will estimate the above population equation to approach the actual value of y. We always know that the actual value of y will not always equal to the expected value of y. There are various factors that can disturb, quote unquote, the actual behavior of y, and therefore we can write the actual value of y is a function of alpha plus beta x plus u. So remember, this is the estimated value of y, this is the actual value of y. So u here reflect the disturbance where there are other factors that can disturb the actual value of y. For example, omission of explanatory variables. There might be other factors other than x that may be affecting y but left out from our equation. This may be because we do not know the factors, or we don't have the data to observe the factors, or we cannot measure them. Second, aggregation of variables. So the disturbance can also happen due to having too many variables, and therefore we need to aggregate them, or we need to group them to become one indicator, one aggregate number. Therefore, eventually we have only an approximation of y, and the discrepancies will be captured in the disturbance term. Due to model misspecification, we might have a misspecified model in terms of its structure. For example, that yt is not affected by x, but is affected by the previous value of x. Since the current value of x is related to the previous value of x, so the estimation of this equation will have some discrepancies, and those discrepancies will be captured by ut. And it can be also from the functional misspecification. Perhaps the relationship between x and y is not linear, but we estimate their relationship using a linear model, so the discrepancy will be captured by ut. And maybe the use of the variables in x or y is measured incorrectly. Maybe we need to use the actual value or the value in percentage. So the measurement of one or more variables in the model, if they are not a correct measurement, so the error will capture the discrepancies. For example, from the auto data that we have earlier, we can plot a relationship between mileage and weight. Logically speaking, the mileage per gallon will have negative relationship with the weight. So we can run a command of scatter mpg weight. With this lfit mpg weight, we can get this scatter plot of mileage against weight. So we have a negative relationship between mileage and weight because mileage will be less when the car has more weight. For the relationship between mileage and weight, as shown by the dot, which is the actual data, OLS will estimate their relationship. Once OLS estimate the relationship between the mileage and the weight, we can get the fitted line as shown in the picture. So going back to our relationship just now, given mileage is a function of weight, and we estimate an OLS to examine the relationship between weight and mileage. So that is all about the OLS regression.